Alright, so continuing from our last video on integration by substitution, we're moving into example K, where we're finding the integral of 3x squared plus 1 quantity times e to the x cubed times e to the x dx. But I can rewrite this. I'm going to write this as the integral of 3x squared plus 1 times, now because this portion, they have the same base, we can write it as e to the x cubed plus x as the power dx. Now I'm going to say that u is going to be that power on e, x cubed plus x. So when I find the derivative of u, I'm going to have 3x squared plus 1 with respect to x, and I've got a 3x squared plus 1. So I can rewrite this now as the integral of e to the u du. And that's fine. Which means when I take the integral, I'm just going to have e to the u plus c, and I can replace u with my x cubed plus 1. So I'm going to have e to the x cubed plus x, not plus 1, plus c. And we're all done with that one. So let's look at L now. We're taking the integral of e to the 3t over 3 plus e to the 3t. So when I do that, I'm going to actually this time let u equal what I have in the denominator, 3 plus e to the 3t. Because when I take the derivative of u, I'm going to have 3 e to the 3t with respect to t. And we're almost at something we already have. What we can do now is divide by 3 and rewrite this as 1/3 du equals e to the 3t dt, and we have an e to the 3t and a dt. So now we're good. So we can rewrite this as 1/3 of the integral, 1/3 times the integral of 1 over u du. Now from our integration rules we've had, when we have 1 over u, that's a pretty simple integral to do. We just have to remember the rules. So we're going to have 1/3 times the natural log of u with respect to, not with respect to u, plus c. Now I'm going to replace u with what we said u is equal to. So we're going to have 1/3 times the natural log of 3 plus e to the 3t plus c, and we're all done with it. Alright, let's move on. So m and n. We have the integral of 3 to the x plus 1 over x dx. Now, I'm going to first split this up. We can do that. We're going to write this as the integral of 3 to the x with respect to x plus the integral of 1 over x with respect to x. Now we can pretty easily find that second part, but the first part is a little bit more difficult. So I'm going to let u equal 3 to the x. If we do that using our derivative rules, the derivative of 3 to the x is going to be 3 to the x times the natural log of 3 dx. So we're going to just replace some stuff. We're going to take and divide by our natural log of 3. So we're going to have 1 over the natural log of 3 du equal to 3x, 3 to the x dx. So in this first integral, we're going to rewrite this as 1 over the natural log of 3, that's just a coefficient, a multiple, times the integral of 1 du. We don't even have to write the 1. I'm going to, just so we can see what's going on. Plus, we can integrate this second part right away. We know the integral of 1 over x is going to be the natural log of x plus c. And we don't have to add another plus c when we finish this first integral here. When we're taking the integral of that first part, we're going to have 1 over the natural log of 3 times, well, the integral of 1 is just going to give us u, plus the natural log of x plus c. We're going to just replace u now with 3 to the x. So we're going to have 1 over the natural log of 3 times 3 to the x plus the natural log of x plus c, and we're done. There's nothing else to integrate. Okay, I'm going to erase a little bit of what we had going on with this problem, just so we can do problem n. Just get that stuff out of n's space. So n, we've got the integral of x cosine x squared times sine of x squared plus 5. This time I'm going to let u equal, I've got 2 sets of parentheses. A little interesting. I'm going to take that second set. I'm going to let u equal sine of x squared plus 5. So that way when I take the derivative, I'm going to get this derivative of sine is cosine. And I have to then take and do the chain rule. So I'm going to have 2x cosine x squared dx, and we're almost there. All I need to do is rewrite it as 1/2 du is equal to x cosine x squared dx, and now I can start my integration. So I'm going to write 1/2 the integral of u du. So I'm going to increase my power on u, so I'm going to first rewrite my 1/2 times u squared over 2 plus c, and now I'm going to replace u. So I'm going to, in fact, before I replace u, I'm going to rewrite this as u squared over 4 plus c. That way I just can not worry about having a mess. We can do that. Now let's replace u. We're going to have, in parentheses, sine of x squared plus 5 squared over 4 plus c. And that's our answer. So now we've got the general power rule for integration. What we say is if g is a differentiable function of x, then the integral of g to the x to the power of n times g prime of x with respect to x is equal to g of x to the n plus 1 divided by n plus 1 plus c, as long as n is not negative 1. Equivalently, we could replace g of x with u and say the same thing. So far we've looked at doing all this with indefinite integrals, but what if we have a definite integral? Now there's a process to this. If we have an upper and a lower bound, we have to change those. Okay? We can't keep them as a and b. Whatever we say u is going to be, typically u is g of x, we then have to plug a and b into our u expression. And those are our new bounds for our integral. So let's look at some examples of what that would look like. So, our first two examples, A and B here, we are going to integrate from 0 to pi over 4 tangent x times secant squared x with respect to x. So, I'm going to start by letting u equal tangent x, because I know when I take the derivative of tangent, when I take the derivative of u, I'm going to get secant squared x dx. If that's the case, now what I have to do is take my x values, our 0, our bounds, our a and our b, and our pi over 4, and I have to plug them in to tangent x. Well, tangent at 0 is going to give us 0. Tangent at pi over 4 is going to give us a u value of 1. So, we can now rewrite all of this. We're looking for the integral from 0 to 1 of u du, which means we're looking for the integral. We can now integrate it. So we're going to increase u's power by 1, divide by that power, from 0 to 1. We don't even have to worry about putting the function we said u was back in. We're going to be looking at half of 1 squared minus 0 squared. So we're looking at half of 1, which is simply a half. Alright, let's look at B. In this case, we've got from 0 to pi over 6 of sine 2 theta over cosine cubed 2 theta. I'm going to let my u this time be cosine 2 theta, which when I take the derivative of that, derivative of cosine is negative sine, so du is going to be negative, and then we have to take the derivative of 2 theta, so negative 2 sine 2 theta d theta. But I don't like that negative, or the 2, because I don't have those in my original problem, so I'm going to rewrite this as negative 1/2 du equals sine of 2 theta d theta. Now, we also have to change our bounds. We had originally 0 and pi over 6, but we need to plug those in to cosine 2 theta. If we plug 0 into cosine 2 theta, well, that'd be cosine of 2 times 0 is 0. So now u is going to be 1. And if we go 2 times pi over 6, that's pi over 3. Cosine of pi over 3 is going to just be a half. So our integral is going to be from 1 to a half, multiplied by negative 1/2 out front, of u to the negative 3, because cosine is cosine cubed in this problem, and it's in the denominator, so we're good there, du. But with our integration rules, we can switch our bounds as long as we take the opposite of this integral. So we can rewrite this as 1/2, the opposite of negative half is half, from 1/2 to 1 of u to the negative 3 du, which if we increase our power, we can write this as 1/2 times u to the negative 2 over negative 2 from a half to 1. So when we plug 1 in, we're going to get 1/2 times, I'm going to bring the u down, so 1 over negative 2 times 1 squared is just 1, so it's going to be negative 1/2, minus, if I put a half in, I'm going to have 1 over negative 2, a half squared is a quarter, which means we're going to have 1 over, just going to make this a 1 over negative half, which, let's just change this to plus positive. When we divide 1 by a half, that's really just 2. So we're going to have a half times a half plus 2. So let's rewrite this. Let's get this down to one number. We're going to have a half times a half plus 4 over 2. And I made a mistake. I forgot to carry this negative through with this first half. So we're going to have 1/2 times 3 over 2, which means we're going to end up with a final answer of 3/4. Alright, let's check out our last two examples. So C and D. We're going to take the integral from 0 to 2 of 3x squared times the square root of 1 plus x cubed. I'm going to start by saying we're going to let u equal 1 plus x cubed, because then du is going to equal 3x squared dx, which we have in this function, in this problem. So our original, we have to change our bounds. Our original bounds were 0 and 2. If we plug them into our u, 1 plus 0 cubed is going to be 1. 1 plus 2 cubed, well, 2 cubed is 8, plus 1 is 9. So our new bounds are 1 to 9. So we're going to find the integral from 1 to 9 of u to the half du. So now I'm going to integrate. I'm going to have u to the 3/2, but I have to multiply by the reciprocal of that, so 2/3 u to the 3/2 plus c. Now, I don't even need the plus c for this. We're going to go from 1 to 9. So we're going to have 2/3 times 9 to the 3/2 minus 1 to the 3/2. Well, 9 to the 3/2, we can do the square root of 9, which is 3, to the power of 3. 3 times 3 times 3 is 27. So we're going to have 2/3 27 minus, well, 1 to any power is just going to be 1. So we're going to have 2/3 of 26, which let's just multiply. 2 times 26, 52. Over 3, and 3 does not go into 52 evenly, so let's just leave it as 52 over 3. Now, I'm not going to have enough time to do D in this video, and I don't want to make a third video for you, so we're just going to skip D. And that is going to end our lesson on integration by substitution.